For homework in section 5.1 about sequences, please do problems on page 447. Problems number 5, 9, 11, 15, 17, 23, 25, 27, 29, 39, 43, 47, and 51. And also, don't forget to do the student project, which is on page 446 at the end of the section, but before the homework problems, where you're told to find the formula for the Fibonacci numbers. And so please go do your homework, and when you come back, I want to talk about it. Now that you're done with homework, let's start with talking about problem number 5. Problem 5 and 9 are fairly straightforward, so I will just show you how it's done. I'm sure you didn't have much trouble getting there. But problem 11, however, is more complicated because you have something that's defined recursively, and you're supposed to go find the explicit formula. Now, luckily, with this particular problem, it's still pretty obvious if you write out a bunch of terms. The bunch of terms, as you can see, once you calculate up to say 5 terms, you see some kind of a pattern. The pattern is equal to 2 to the power n, okay? Except, like, for example, if you calculate 2 to the power n, then before, and then 8, and then 16, but it's missing 1. That's all the difference there is. So the pattern that it appears to be is 2 to the power n minus 1 minus 1. For an, that is. And there's an n minus 1 because a1 is 0. So it's off 1. But anyway, if you adjust that, you will notice that it will fit the first 5 requirements. However, just because it fits the first 5 requirements doesn't necessarily mean that it is the right formula. I mean, we have to prove that it has to fit all the time. So, but the proof, however, is quite straightforward. We do something similar to mathematical induction, and what happens is that this is the formula we guessed, right? Okay, here's down here, this thing. Okay, this is the formula we guessed because it fits the first five items. But does it always fit? So we just check to see if this formula fits the recursive formula. What was the recursive formula? Yeah, up here. The recursive formula says this. So we just simply plug it in. Let's see, can you see it better? Okay, we will plug it in, okay, and see if it does fit. That is an minus 1 by our definition end up being satisfy the recursive formula for an? And it does. Once we plug it in and do a bit of algebra, it does equal to an, like it says. That is, 2an minus 1 plus 1 does equal to an by our formula, which proves that this formula, the explicit formula, completely satisfies the recursive formula from 1 to wherever you want to be, and therefore it is the right answer. Now next, let's look at problem 15 the same way. Now we're supposed to write the formula for the sequence, so we write out a few terms, and it appears that the formula is something like an is just 2 to the power n. However, just because it looks that way the first few times, doesn't mean that it's actually necessarily the right answer. But we can prove it by plugging it into the original formula to see if it satisfies the original formula. So an plus 1, we plug it in our formula, and does that equal does it fit that formula? It does, and therefore it is the right answer. And that is, our guess is correct. Next, let's look at problem 17. Problem 17 looks kind of puzzling, okay? So let's write it out, and if you write it out, you come up with a bunch of numbers that doesn't seem to is growing fast, yes, but what is the discerning pattern for it? So then we write it out in terms of the formula itself. The recursive formula, what happens then, you have 1 plus on this side I'm talking about, see, then you end up being 1 plus 1, 2 plus 1, 3 plus 1, right? That in other words, the n increases, and as you multiply, things get the multiplication piles up each time you go up. So that shows you the pattern. And the pattern then, when you stare at that long enough, you realize the pattern is something like this. Down here, see a of n equals to 2 times 1 plus 1, 2 plus 1, all the way up to n minus 1 plus 1. And so then you derive your pattern, okay? And that would be, that might be the answer, but you still need to prove it. And to prove it, of course, is you apply this formula to the original definition to see if it fits. See, here's the definition, here's the formula. So the definition says an times n plus 1 over 2. You plug in an and clean it up a little bit and find out it does equal to an plus 1 if we follow the formula that we designed. And therefore, the formula is correct. Next, let's consider problem number 27, when we have n squared over 2 to the power n. That is the same as calculating x squared over 2 to the power x as a function. Remember, the sequence is the same as the function, except its domain is restricted to the natural numbers. So if the function converges, then the sequence is going to converge right along with it. So how do we calculate the function convergence? That is something we did, I think, in Calculus 1. Okay, remember how to do this kind of thing? It is an infinity over infinity situation. Therefore, you will take the derivative by applying the L'Hopital's rule. And also remember how to take the derivative of b to the power x, where b is a number. That's not done a lot, so sometimes one might forget. So then to take the derivative is the same as e to the power x, except that you have to tag on the natural log of b. So once you've applied the L'Hopital's rule, then everything comes out nicely to be 0. Therefore, the sequence converges to 0 as well. And that's 27. Now next, let's look at problem 29. Problem 29 is some kind of a fraction. Okay, and that might look, there's the square root sign, which might look confusing until you remember how this kind of limit is done. If you turn it into an x, which is taught in Calculus 1, the way you do a fractional limit is you divide the variable out on top and bottom. So you divide by n on top and n on the bottom, and turn a fraction into something like this. And when you do that, then as n goes to infinity, 1 over n disappears, becomes 0, so you are left with 1. And that is the quick answer. And next, let's look at problem 39. Now, problem 39 says that an is equal to the square root of 2 times the square root of an minus 1. So you have to take the square root every single time of the previous thing. So things are getting, a ton of square roots in it, and then getting operated on. So then, so that looks very puzzling. Well, does it converge? And how do we prove that it converges? If it does. So let's assume that this converges, just to see if it converges, what would it be? So if this thing converges, okay, big if, then the limit exists, then limit of an is the n approach infinity, of course. As the limit of an is the same as you remember, the limit can be split up, so that is just the limit of square root of 2, which is just square root of 2. And then the limit of square root of an minus 1, and n goes to infinity. Being that n is going to infinity, right, the limit of an minus 1 is the same as the limit of an, so let's call it L. That's the trick taught in the last example in the book, 5.6 or something. Anyway, so or maybe a different example, I don't know. But the point is, being that they are the same sequence, they go to as n goes to the infinity, both go to the same limit. So they both equal to L. L equals to square root of 2 times, this goes to square root of L. Yeah. See, because it's inside the square root, so it goes to the square root of L, and from that we can calculate that this is multiplying, right? So then the square root, you divide the square root of L out. So the square root of L equals to square root of 2. So the limit equals to 2. However, this is only true if the limit exists. If the limit doesn't exist, then what we just did made no sense and is worthless. Okay, so now that we calculate that if the limit exists, it would be square root of 2. And then now let's make sure that it does. To prove that the limit exists, we'll use the monotone convergence theorem, which states that first we'll prove that the limit is decreasing, okay, and then we'll prove that the limit is bounded. A decreasing bounded sequence, it converges into some limit. So to first, let's say that it's bounded. How do we prove it's bounded? Then so the bounded is like this. The an will quote this original definition right here, where an equals to square root of 2 times square root of an minus 1, right? And so if this is where an minus 1 is bigger than 2. Well, we start out with a1 equal to 3, so the first one, this applies anyway, is bigger than 2. Then, if an minus 1 is bigger than 2, then an equals to this thing is going to be bigger than square root of 2 times 2 times square root of 2, because an minus 1 is bigger than 2. Okay, and we're starting in the beginning, meaning that a1 is 3. That's bigger than 2. So for each one that's bigger than 2, the next one will, for each an minus 1 that's bigger than 2, the next one will also be bigger than 2, which means they will all be bigger than 2. Okay, it started out bigger than 2, and each one, the following one will continue to be bigger than 2 forever. So therefore, the sequence is bounded by 2 in forever. So it's bounded on the it has a lower bound. So that's the first thing we need to do. And then the second thing is we need to show that it's decreasing. The way to show it's decreasing is we'll do a fraction. I don't have space there. I'll do it on this side. So let's consider the fraction of an over an minus 1. What does that look like? That is, by definition, the square root of all the square roots, okay? An minus 1 divided by the an minus 1. And when you do all that, that equals to the square root of 2 an minus square root of an minus 1. And you notice that as we mentioned, an minus 1 is bigger than 2. Each one of them. Each an is going to be bigger than 2. Therefore, this term is bigger than square root of 2, which means when it's the denominator, it becomes smaller than square root of 2. Okay, which equals to 1. Therefore, the fraction an over an minus 1 is going to be less than 1. If it's less than 1, then it is decreasing. Okay, yeah, right. Anyway, so it's decreasing, and therefore, so it is a monotone function that is decreasing monotone function bounded on the bottom by the number 2 or something. Therefore, the limit exists. And as we calculated that if the limit exists, then it has to be 2. And that concludes this problem. Next, let's look at problem 43, where an equals the sine of n, and then sine of 1 over n. How would that come out? Now, when an is, what we're going to do is turn this into a function. And being that we have n and then 1 over n, we will turn it into a function f of x, where x will let x equal to 1 over n, like this. And that way, as n goes to infinity, x goes to 0. Because we're more comfortable dealing with 0 than infinity. So then, so f of x equals to sine of 1 over x, and then sine of x, which is the same function, right? Just because the way is symmetrical. Yeah, I mean, so to calculate n goes to infinity, all we have to figure out is what happens to this thing when x goes to 0. Now, to do that, first we are going to establish this fact, which is sine of x. The sine of x is going to be less than x if x is bigger than 0. Now, how do I know that? This statement, this is proved in Calculus 1, but in the first chapter. But the idea is that you draw a unit circle, okay, a part of it, a slice of unit circle, and this is your x. This is x, and being that this is 1, okay, this length here is sine of x. Whereas this arc, the length of the arc is x. That is the definition of the radian. So then, as you can see, the sine of x is the right angle triangle, which is less than the hypotenuse of this right angle triangle here. And the hypotenuse is the, what is called, secant, I think is called. But anyway, it's shorter than the x. Therefore, sine, that's how this relationship is established. Sine of x is less than this thing in the middle, which is less than x. Okay, the secant is shorter than the arc because of the geometric axiom that says the shortest distance between 2 points is the straight line, and this is a straight line. That is not a straight line. Therefore, sine of x is less than that. The hypotenuse, which is less than the arc. And so anyway, so we got this thing going, and this is actually true on the negative side as well. So we'll just say that this is, always the case, and therefore as well, in our situation, we only care about the positive side. Yeah, well, whatever. The point is then sine of the sine of n. So then when we look at this function, the sine of 1 over x times sine of x as x goes to 0. Okay, remember, we're doing x goes to 0. Because x goes to 0 and goes to infinity. So then this one is less than x squared, which goes to 0. Okay, as x goes to 0, everything goes to 0, and that's the end of that problem. So the only hard part about this one is you have to remember the sine of x is less than x. The last problem we're going to talk about is the Fibonacci series. The Fibonacci series is fairly famous mathematical series. Sequence. Fibonacci sequence is a fairly famous one, and that's also very simple. It just says f of 0, let it be 0. F1 is just 1, and then from that point on, the next one will be the adding up the previous two, which seems easy enough to do, until you realize, okay, that's fine, but is there any way we can come up with an explicit formula for it? Well, then, so that's what we're going to do right now, okay? The explicit formula doesn't look easy at all, because for one thing, you're dependent on two things, two previous objects. How would you do that? So the way to do it is first, we'll write out some samples of it. So I did that, and it got me total of nowhere. So we'll skip it. And number 2, then let's look at step 2, part A. Part A wants you to consider the sequence where xn minus 1 equals to axn. And so I did that too, and it got me a total of nowhere. So let's skip that also. And finally, it says that use the result of part A as motivation. Well, I did. I did not get motivated from it. But the point, however, is that is the next part. That's when it actually happened. Let's say that there is a formula. Okay, let me get my notebook. Okay, now let's say we got So Fn, let's just say it does. How do we know it does? We don't know, but let's just say it does. Okay, let's say the f of n is something like this. Fn equals to c lambda n, such that, well, then of course Fn minus 1 would be equal to c lambda n minus 1, and then similarly Fn minus 2 equals to c lambda n minus 2. All right, and then we will fit this thing into this formula. The Fn equals to Fn minus 1 plus Fn minus 2, and then we'll come up with some kind of a thing. So we're going to solve this equation where Fn equals to Fn minus 1 and Fn minus 2 for lambda, I guess. So let's write that out. So Fn is c lambda to the power n, which equals to c lambda n minus 1 plus c lambda n minus 2. The first question we have is, where do we get this idea of lambda to the power n and stuff? Did we get inspired by that little bit of stuff we did earlier? Not me. I haven't seen any inspiration. It's just something that somebody came up with, and to see if it works, I guess. I don't know. But anyway, that's what we're going to do. Okay. Now, if we can come up with a lambda such that this equation holds, then this particular formula will satisfy this condition. All right, so then Fn so let's figure out what if there's any lambda where this condition holds. So luckily we have c on each part, so we can get rid of the c, and we get lambda n equals to lambda n minus 1 plus lambda n minus 2. How do I know this is pronounced lambda? I don't know. I could be wrong here, but let's ignore that. Okay, I'll look it up later to see what this letter, how to pronounce this thing. But somehow my brain says lambda, so we'll just go with that for now. It could be wrong though. But anyway, so we'll divide it out. Okay, divide something out. Let's divide it out. We get one. Get rid of the whole thing. So we get 1 equal to lambda to the power minus 1. Plus lambda to the power minus 2. Okay, that gives you that gives you a quadratic formula, which is lambda squared equals to lambda minus 1, I guess, or plus 1 or something. Plus 1? Why is it plus 1? Well, actually I wrote that wrong, sorry. It's equal to lambda squared minus lambda minus 1 is what I got. And then eventually you get the answer of lambda then equal to the good old quadratic formula, plus or minus square root of 5 plus 1 over 2. All right, so we got the value of lambda. Now at this point, we know the f of n of c lambda n, as long as lambda is this value, okay, it will satisfy this condition of this condition of Fibonacci, that f of n is which equal to, if it equals to c lambda to the power n, where lambda is either the plus or the minus value, then for any c actually, then f of n equals to the previous one, fn minus 1, n plus fn minus 2. Okay, so far so good. But we don't know, but it doesn't necessarily satisfy the initial conditions. Now, so then and that's true for either lambda. Okay, that is so how now so we got a function that satisfies this thing in the sequence. The question is, how do we get it to satisfy the first one? So we're going to build a trick. So we'll build a different another function that we're also going to call it f, for just because we're lazy and don't want to call it something else. But so we are going to build a new function where f of n is equal to c1 lambda 1n plus c2 I'll stand over here, plus C2 lambda 2n, where lambda 1 is one of the roots here and lambda 2 is the other root. Where but C1 and C2 need not be the same function. Now this function will also satisfy this equation because it's being added. So it's basically two of them. You take one of these, which is one of them is C1 lambda 1, and then the other one is C2 lambda 2. When you add it together, the new function still satisfies that requirement. See, because that is an addition and the new function is an addition. So it will still work. Now, having said that, then we need to, now the reason we're doing this is because then we can figure out some way to get this new function, which is a manipulated sum of the old function. We will use this thing to find C's that satisfies F0 and F1. So we are going to plug that in so what is F0? Okay, now f of 0 for this function, then n is 0, okay, and then so these things becomes 1, and then so f of 0 is C1 plus C2 equal to 0. That gives you the relationship between C1 and C2, which should help us figure it out. And then secondly, we have f of 1, which has to equal to 1. Okay, that equal to C1 lambda 1 plus C2 lambda 2. Now, lambda 1 and lambda 2 are these two values, the plus and the minus of whatever that is, lambda 2. Now, if you do that, then, and then so now we have a simultaneous equation and two variables and stuff. And when you plug stuff in, I mean, C1 is just negative C2, plug that in here and calculate lambda 1, lambda 2. And when you're all done, you get something like C1 is then equal to 1 over square root of 5. And then C2 is the negative of that value, equal to negative 1 over square root of 5. And at that point, therefore, so then the Fibonacci series can be explicitly represented by the formula that is 1 over square root of 5 times 1 plus, what is that? 1 plus, this is lambda 1, okay? 1 plus square root of 5 over 2, lambda 1 to the power n minus 1 over square root of 5 times, where's my square root? Okay, 1 minus square root of 5 over 2 to the power n, where this one is lambda 1, okay, and that is lambda 2. So notice that the important point to remember is that we generate a new f of n to replace the old one. Okay, the old one is actually in order to calculate C1, the new one satisfies the same condition as the old ones because it's just two of the old ones added together. So that is as you can see, extremely clever way of beating around. The question is, how do they get this thing to start with? Well, I don't know, just play around and hope something comes out. And so that's what happened. And when you play around with enough tries, so sometimes you hit the basically you hit the jackpot by starting right here, and then have a clever manipulation of using both roots. Okay, you use lambda for both roots, and then eventually here comes our answer, and that answer is correct because I googled it to make sure. And yeah, so that is the. Yeah, as you can see, the Fibonacci formula is really complicated, but the answer is going to be very simple. It's just a bunch of numbers, right? It's never going to have square root of 5 in there, but somehow that's all taken care of. When you plug in the numbers, out comes all the square roots are taken care of, and out pops some neat whole number. All right, let's see. Now the rest of the problem, such as the limit of fn plus 1 over fn equals to some value, is I didn't do that because that doesn't look very exciting. It just, yeah, anyway. So then and what's worse is the limit has a name to it. It's called the golden ratio, which is something that is being used in history as some kind of a fancy term, I guess. But in reality, and nowadays our golden ratio, as this video shows you, is called 16:9, which is also shown by my board. See, and nowadays we don't care about the golden ratio anymore, I don't think. Anyway, so that's what's the next thing? Oh, the next thing is talks about something about how sunflower grows. It's yeah, well, we don't care about that at all because I mean, never mind sunflower. We haven't even figured out why ants have 6 legs and we have 2. You know, it's a number. What can I say? So that marks the end of this section.